I want to prepare you for something crazy that might happen when you're dealing with square roots or any kind of roots. Consider this equation. Let's try and solve it. Well, I guess the first thing we'd do is divide both sides by 5 to try and isolate that x squared, wouldn't we? Or to isolate the x itself. That's not too bad. And we get x squared equals -1. Okay, straightforward. Now, how do we get rid of that 2?
Now I use my secret weapon.
We use the rooter, remember? Of course, if I do it on one side, I have to do it on the other. Well, on the left side, the square root of x squared is x. On the right side, the square root of -1. Uh-oh, obviously this could happen, but we can't have the square root of a negative number.
I knew I should have checked your showboating globetrotter algebra.
So now what are we going to do?
Yes, you're in deep doo now.
Well, as you can see, this can happen.
Toto, I have a feeling we're not in Kansas anymore.
So that we can at least discuss these answers to such an equation, we're going to introduce something different. We're going to introduce I. Nice to meet you, I. I is the square root of -1.
Welcome to Fantasy Island.
We call him I because he's imaginary. Of course, we know the square root of a negative number doesn't exist.
Illogical.
Okay?
I know you are, but what am I?
Well, I is the square root of -1. Now, consider that up till now, we've been dealing with numbers that we want to say are real. They actually exist. If we could write them down, we called them rationals, didn't we? Fractions we could write down, and repeating decimals we could represent, and we could write them down. So we called those rationals.
Illogical.
Okay? Some we couldn't actually write down, but they were real. They were irrational real numbers. For instance,
To infinity and beyond.
the square root of 2, recall, we couldn't really write it down. It just went on, and there was no pattern. Pi, for instance, it actually goes on forever and ever and ever. So we call that irrational. But both rationals and irrationals are real numbers. They actually exist.
Certainly.
Okay?
There's something screwy around here.
Imaginary numbers do not exist, but we're going to discuss them. So, imaginary numbers involve, of course, what we just told you, I.
Fascinating.
They're not real.
My paw will coin you.
Okay, which means, of course, that they don't actually exist. But they seem to crop up in these equations, as we saw at the beginning.
Pay attention, son. This is for your own good.
So any number of the form a plus bi,
Holy alphabet.
there's a lot of letters. What I mean is
Allow me to demonstrate.
3 plus 5i, or 3 minus 1i, or 3 minus I, of course that's the same as 3 minus 1i, is going to have to be part real, that's the A part,
Illogical.
and part imaginary. And anything that's part real and part imaginary,
Nerd alert!
we're going to call complex. That's a complex number. Now, if you're truly dealing with complex numbers, consider the exponent of I will have to be 1. Because I
That's the fact, Jack!
I is the square root of -1. So, if we square it, in other words, if the exponent isn't 1, the basic definition of square roots, if we square a square root, what will we get? I squared will be -1, and then we won't have a complex number anymore, will we?
Just when I think you've said the stupidest thing ever, you keep talking.
Consider all the other powers of I.
Pay no attention to that man behind
Okay, of course if there's a 1, we don't have to pay any attention. I squared would be negative 1, as we just showed you. I to the third, well, let's break it up. I to the third would be I squared times I. Well, I squared is negative 1, and I to the first is just I, so I to the third would actually equal a negative 1I. And that would, of course, make it complex, because the exponent would turn back into a 1, wouldn't it? I to the fourth is I squared times I squared. Now, I to the fourth is very special, because I squared is negative 1, and each occurrence of that, if you have a negative 1 times negative 1, we're going to get a positive 1. So any time you have I to the fourth, you're going to end up with a positive 1, and usually, of course, you can throw out a 1 when you're multiplying.
Here's looking at you, kid.
Okay, so keep an eye out for these, and we'll simplify them to the numbers that they're equal to. Let's mix these facts with the rules of exponents.
Let's play. Here we go.
And I want you to simplify this expression. I to the 102th minus I to the 49th. Holy mackerel. Well,
Are you pondering what I'm pondering?
I always say look for 4s, because remember what I to the fourth is 1. So anytime you have an I to the fourth or a factor of I to the fourth, you can throw it out. Well, I to the 102th is really I to the 100th times I to the 2th, isn't it? Because we add exponents. And I to the 100th is a multiple of 4. It's I to the 4th to the 25th, because you know your rules of exponents with parentheses there, you multiply. So this portion of it is just 1. And 1 to any power is 1. So now, you've broken it down to just really I to the second.
It is a lie.
And that's minus 1. Okay, now let's try and get this one down. Once again,
What would you do with the brain if you had one?
let's look for 4s. What do you smell? I to the 48th. Well, that's going to become a 1, because it's I to the 4th to the 12th, and I to the 4th is your buddy. Remember, we're looking for I to the 4th, and 1 to any power is just 1. Okay? So all this simplified using your rules of exponents. It's a good exercise.
And that's how she wrote.
To minus 1 minus I. Let me give you another.
Well, why don't you fix it, meathead, huh?
Let's simplify this. I to the 72th.
Now I use my secret weapon.
We're looking for I to the 4ths. And it goes evenly in, doesn't it? So that portion of it, I to the 4th to the 18th, because 4 times 18 is 72, is 1 to the 18th, which is what? Just 1. And this portion of it,
Gee, let me think.
well, let's take the biggest multiple of 4 out, and we'll get, okay, I to the 4th to the 6th. Once again, 1 to any power. Now, do you recall what I squared is?
I know that, dude.
It's negative 1. So all this becomes what? All this becomes, okay, and that's the answer.
Believe it or not.
It's a good exercise in the use of I and the rules of exponents. Now, unless you square it, I can be treated like any variable.
Now what am I gonna do?
For instance, in this problem, all we're going to do is add like terms. 3 and negative 2 become 1, and negative 4 and negative 3i added become negative 7i, and since we don't have an I squared, or I should say since we do have an I to the 1th power, we're all done. Okay, so just treat it like any other variable unless you get a power higher than 1 on your I. It's good use of review of dealing with variables.
I have a feeling Some bad stuff is about to go down.
Remember, when we try to subtract things, we end up changing the sign of the whole second expression. So I changed that to addition and changed the signs of everybody in the second group, and now it just becomes adding like terms again. 3 and 2 become 5, and minus 4i and positive 3i become a negative 1i, and of course we only write the negative I.
Any of this sinking in, boy?
Okay? I really think most of the reason we cover complex numbers is to review all the other rules.
I'll get you, my pretty.
For instance, in this one we're going to review distribution. 5i times 4 is just 20i. 5i times what I would say is negative 7i becomes negative 35i squared. Now wait a minute. I squared is negative 1. Okay, we have to always have I to the first power. So we'll simplify that. And we'll get negative 35 times negative 1, or... And now we have our answer. Multiplication is sometimes going to lead us to these I squareds.
Do that again.
Now this one is kind of a FOIL problem. Let's take the 2 and distribute him to both of the second expressions. 6 and 4i. And now we're done with the 2. And now we'll take the 2i and multiply him, or distribute him to the 2 in the second expression. That's going to be 6i. I like to write it underneath his buddy because they're getting together later. And 4i squared. Now, wait a minute.
Come on down.
He adds, he just comes down. The 4 and 6i become 10i, but here we have an I squared. Remember, I isn't negative 1. I squared is negative 1. So we'll have a negative 4 there. And then he can get together with the 6. And we'll have a final answer.
Woohoo! Come to Papa.
Okay? Do you remember when we simplified radicals? Well, we broke them into the perfect squares, and then what was left over? The garbage. In this case, the largest perfect square is 9. That leaves me with a 2, and this radical simplified becomes 3 radical 2.
Whoa! Someone smells stinky!
What are we going to do here? We've got an imaginary number because we've got the square root of a negative number. Well, pretty much the same thing. We're going to use our perfect squares, but this time we're going to throw in somebody else. Okay, you see there's a new one in the middle. We've got the perfect squares, and the new one
Welcome to Fantasy Island.
is the imaginary part. And we still have the leftovers, and they're still last as appropriate. In this case, the perfect square is 9. The imaginary part, of course, is the square root of -1, and the garbage is the same. So the answer is 3
Fantasy Island.
I square root of 2.
Transfer of data is complete.
Pretty much the same thing, except that you take out the -1, or the square root of -1, and you get I.
Direction unclear. Please repeat request.
We'll do one more. The perfect part, the imaginary part, and the garbage. Now what are they? The perfect part,
Welcome to Fantasy Island.
the imaginary part, and the leftovers. Think about it. The perfect part, 25. The imaginary part,
Fantasy Island.
It's always the same. And the leftover. Now, it's always 3 steps. 5,
Fantasy Island.
I, radical 3. It's pretty much the same thing, isn't it? Except we have that imaginary part that we have to take out because it's a negative square root. Okay?
Does everybody know what time it is?
It's time to go do your homework. And please do it right away. Don't wait till the last minute.